Hi and welcome to another video documenting the development of the ME442 engine management system. In this video we're going to be covering the precision timing module. This is the part of the engine management system that is responsible for dealing with the scheduling and the firing of events. So its core functions are to configure and track the triggering method. So it's to accurately track the trigger wheel. So if you have a 36-1 or a 60-2, its main function is to accurately track that triggering system and therefore be able to generate from that the engine's position, and you'll be able to set within the PTM configuration the pattern you'll be using, the amount of revolutions per an engine's cycle, so you can define if it's 360 degrees, 720 degrees and so on. You'll also the PTM itself also enables events to be scheduled and also to allow events to happen for a certain length of time. And it can also raise callbacks to your other processing chains. For example, you might want to carry out a PID calculation every 10 milliseconds, or for example, every 10th revolution of the engine, apply a correction based on acceleration, an example. So its initially features, well, initially it's going to support the 36-1 and 60-2 trigger wheels. We will be adding Japanese trigger wheels quite quickly because some of our clients have requested that we add certain patterns, and so the RB25 and a few of the Nissan and Subaru patterns will be added out of the box relatively quickly. CAM patterns, it will support straight away the Ford Focus ST170, the Mazda BP series, the Renault series, and a single lobe cam. The PTM allows up to 96 events per rotation, so that's 96 individual events you can schedule per rotation. So this could be, for example, on a 4-cylinder engine, you would probably have 2 coil events, one at 0, one at 180 for a wasted spark setup, and 4 injection events for example, fully sequential. So, a 4-cylinder engine only uses 6 of these events to have the engine running, leaving 90 events for more advanced things, which we'll go through shortly. In terms of accuracy, we will have a 1 microsecond duration event, so you can set an injector, for example, to run for 4.752 milliseconds, and it will run to that, and a 0.01 angular resolution, so you can set your ignition angle, for example, to be 100.74 degrees before TDC. If you don't know why you have something that extreme, but you can. And it will support and synchronize and schedule events at over 20,000 RPM. Currently, it will be a scriptable configuration within the MEITE, but we will plan to have it a lot more simple. So you'll be able to actually draw your trigger wheel in an application within the MEITE and actually place on there various points. So you'll be able to say, well, this is the pattern, and I want event A's to be scheduled here, event B to be scheduled here, and also timing markers and resync markers and so on. And you'll also be able to record what's on the engine using the scope, so it'll actually record the crankshaft stimulations it gets via the crankshaft sensor, plot those, and allow you to then draw the cycle of the engine on there and mark where cylinder 1 TDC is and so on. So a PTM node, which when you design the processing chain for your engine, either you're using a standard off-the-shelf processing chain which will already have all of these defined for you, or you're defining a processing chain from scratch. You'll need to add PTM nodes to actually make outputs do something, because without a node there'll be no output control, there'll be no output stimulus, so nothing will happen, there'll be nothing synchronized to anything. So first of all, a PTM node handles 1 event per rotation, so you can have up to 96 nodes on your processing chain in totality. Each PTM node has an angle and a duration, and you can set the angle within the engine's domain of 0 to 720 or 360, depending on how the PTM has been configured. And of course, a duration. So for example, when you're looking at a fuel injection map, the important thing is the duration, how many milliseconds. The angle, not so, but again, it can be mapped, but the angle could, for example, be fixed across the entire engine speed and so on. And for ignition, well, the angle is the critical thing. You change the angle, maybe looking that up from a table, and the duration would generally be fixed or for dwell or looked up from a very basic 1D table based on battery voltage. Every PTM node resolves to a logical on or off of a chosen output on the ME442. So, for example, you have a series of outputs, be those coil drivers or injector drivers or half bridge drivers, you'll be able to tell those pins to go on or off in turn with each event, or at the end of an event, or at the end of a duration, or the middle of the event, or and so on. So you really have a lot of flexibility. So let's have a quick look at an example of an ignition chain using the PTM. Now this is very basic. There's no corrections for coolant temperature or ignition or rev limits or anything. This is a very basic get you running engine. So first of all, there's the base offset angle. Now this is a number. This is a user-defined variable, and in this case, the user has defined that to be 35. So on a ZTEC, it would probably be 90. And within your PTM configuration, you would say, we'll come back to this, but the base offset angle is just a variable that the user has created, and he set it to 35. Down here we can see ignition table 1 angle, which is a 2D table with 32 by 32 columns and rows, generated from RPM and load, and it outputs as an ignition angle in degrees. And you can see here that what we've done is we've actually added the base offset angle to the ignition angle with the generated data from this 2D table here, added them together, and the output that is then, so for example, this table could generate 12 degrees. We add them together, and it's then passed through here as an angle to PTM, to the PTM. Now, what you can see here is the user's created 2 PTM nodes. He's created PTM, and he's labeled PTM1, and he's labeled it ignition A. He's set his trigger configuration, and that would be within the separate configuration window to define various features and cycles. But he's made a configuration file, and he's enabled that configuration file user 36.1, which tells us it's probably a 36-1 trigger wheel. And what he's done here is he set it to be the ME442 output coil driver 1. So that's a physical pin, a physical connection on the ME442, which in this case is a coil driver, so it's a high current ignition driver. Down here he's created his second node, and he's labeled it ignition B, again using the 36-1 trigger wheel configuration, and he's labeled it coil 2. So we're obviously looking at a wasted spark setup here. So on a 4-cylinder wasted spark setup, as you can probably guess, you need these events to happen 180 degrees apart. They need one to fire near TDC of number 1, and one to fire when number 1 is near the bottom, and obviously number 3 or number 2, whatever it is near the top. So what you can see here is they've created another variable, second ignition events, and they've set it to 180. Now, if it's an odd fire engine, of course, this number could be different, but it's an even fire engine. It's for example, a Ford ZTEC, and they've set it to 180. So what you'll see here is, first of all, you've got your base offset, say 35 degrees. You've then got your angle that's been delivered, and this might be, for example, 10 degrees. So you've got 45 here, and this is fired straight into here, into the PTM A, ignition A. If we follow this output from this adder down here, you'll see it goes into the second adder with this 180 to give you that 180 degree offset. So it's going to fire 180 degrees later, and again you can see this angle being passed into the PTM. The next thing that we'll be looking up when running the PTM is the PTM for every node. It needs a time, so it tells it when to happen, and it tells it for how long. Now, for ignition, you can set a node to happen at the end of the event. So if the time here is 4 milliseconds, you can set it to fire when those 4 milliseconds have elapsed. So what it will do is it will actually start turning this event on. It will calculate the amount of degrees before to reach this time of 4 milliseconds and begin the event there. So you can set an event to happen at the start. For example, fuel, you could set it to turn on at the angle and stay on for the time, or you could set it, in this case for ignition, to turn off at the angle but stay on for the time before that point. And again, that would be within the configuration of each of these PTM nodes. So the time for an ignition event would be dwell, and in this case it's based on battery voltage, so more battery voltage, less dwell, and this would be a one-dimensional table. So this one-dimensional table here the user's created and called ignition dwell is passed because they're both the same. Both drivers require the same amount of dwell to fire the ignition. This is a symmetrical system. So you'll see here that this time in milliseconds is divided across to both PTM modules. So you can see here how this ignition chain would run an engine. It's getting its angle from its ignition table, a 3D table here, and it's getting its dwell from this 2D table here. So everything sort of works and is very fluid and very easy to set up. And as I say, these tables will be predefined, these PTMs will be predefined as a collection of tables. So if you wanted to create just a basic ECU based on a 4-cylinder setup, we would mirror a series of off-the-shelf engine management systems like an MX600 or an i44 from Vipec, and allow you to just create a new ECU project and preload these processing chains and PTM configurations to make the setup and running very easy. So it would just be a case of double clicking on the various tables and mapping those various tables from within the MEITE. So the next thing to look at is a diesel engine. Now the great thing about this is the flexibility. Because we have these PTM nodes, we have pure flexibility. So we don't want to run a petrol engine anymore, we want to run a diesel engine. And a diesel engine in this case has a main fuel pulse, and it also has a secondary fuel pulse, a small pulse afterwards to help with emissions. And it might have several pulses, but in this case we're only dealing with 2. So first of all, we have to note that we have 2 PTM nodes, but these PTM nodes actually share the same output. They both share, and the ME442 doesn't have GDI drivers in it, but for example it does in this, and it shares the GDI1 driver, the 70-volt GDI injector driver, and the second node also shares GDI1, which means that both of these will be firing the same output pin. They'll both act upon that same output pin. As you can see, first of all, the system looks up the main fuel pulse from a 2D table, 32 by 32, RPM and load, and it outputs FP1 quantity in microseconds. So bang, that goes straight into the PTM, and that's calculated every cycle, or however often you set it to calculate this node on the processing chain in hertz. So it calculates this and fires that in at a time. Next is the main fuel angle. And this again is looked up because in a diesel it does matter, and we're basing this on RPM and load again, and we're deriving from that a main fuel angle. And so we're passing to this first PTM node a time, a quantity to have the injector open for, and an angle to have the injector open for, and you can see these two passing into each other here. Now this is a very simple diesel engine, and what we're going to do is we're going to have our secondary fuel angle 12 degrees later all the time. I don't know why they would do that on this engine, but we have. You could of course have a secondary fuel angle adder, which could look up from another table if you liked, or a 1D table that, for example, calculated on RPM changing RPM rate or something like that. But no, in this example we are going to just stick to 12 degrees fixed latency on so the second event will happen 12 degrees after the first event. We add these two together here and pass them to the second PTM node. What is going to change though is the secondary fuel quantity, the amount of time we're going to fire this secondary pulse, and it's going to be a 1-dimensional table, and we're going to look it up purely on load. So if there's lots of load, we're going to put in a very large second quantity. If there's not much load, we're going to put in a very small secondary quantity. So you can see these two PTMs working together here. They'll fire the big pulse, and then 12 degrees later it will fire that same output again for a different amount of time. So you can see here how diesel control can be realized very quickly by using the flexibility contained within the ME core and the PTM modules. So planned features, well, one thing we want to have is user definable trigger patterns with a scope mode and a draw mode. There are a few other things we're thinking about adding from user definable PID lookups based on the PTM timing, active sync tracking, and a few other tricks we're going to be adding, but those are still very much planned. The main thing first is to get the 36-1 and 60-2 support, and of course as people request more trigger patterns and we can be provided with vehicles or decent scope data, we'll be able to then actually build tracking algorithms for each of these patterns as they come in. That's all for this video. I hope it's been informative, and we'll have some more later this week. Cheers.